Hello everyone. We are going to look at section 3.2, determining empirical and molecular formulas. The learning objectives for this section, first of all, compute the percent composition of a compound. Secondly, determine the empirical formula of a compound. And then finally, determine the molecular formula of a compound. We are going to be using the mole concept extensively in this section. So if you don't feel comfortable with what you learned in section 3.1, please go back and continue with that before moving on to section 3.2, because again, it is very much based on the mole concept. What we'll be looking at here is if we are able to know information about how much we have in mass, can we change that to the mole concept? We're essentially putting some numbers to some of the ideas we first introduced with Dalton's atomic theory in module 2, but we needed to really have the mole concept in order to do that. So instead of basically deriving those ideas, we're putting them into practice here with the mole concept. So we can find in some experiments how much we have of particular elements within a given compound. We have ways of separating out certain compounds or certain elements in chemical processes, and we'll actually be doing something related to that in a lab activity very, very soon. When we do this, we can find what's called a percent composition. And this is defined as the percent by mass of each element in the compound. Okay, so when we say percent composition, that is what we mean by that. So a couple of examples here. So if you want to know the percent composition of hydrogen, you would find the mass of hydrogen in the compound divided by the mass of the whole compound, and then times 100%. So for example, you might have 2.5 grams of hydrogen in a 10-gram compound. You do that calculation and you get 25% hydrogen. So when we do this, we're comparing masses. So it doesn't say mass in the definition or in the name percent composition, but that's essentially how we're defining that. Okay, so there's an example here of, if you're given masses, can you find the percent composition? So feel free to look at that if you would like to. One way we can do this is we can decide, well, if we know what the formula is of a compound, we should know what its percent composition should be by taking that formula and taking the masses that we have. Essentially what we're doing here, we're doing something very similar to what you did for section 3.1, where you were finding the molar mass or the formula mass of a compound, but we're taking it one step farther and saying, well, of that, how much is from each of those elements? So for example, if we look at ammonia, you would be able to do this if you were comfortable with that previous section. It kind of walks you through it here as well. So you look up nitrogen, you look up hydrogen, you have 3 of those. You find from that the formula mass. Okay, so that's how you get this number, is that's the formula mass. And then you say, well, what was the nitrogen? It was this 14.01. You divide that and then times 100%. So that's how you get the percent composition. Same thing for the hydrogen. So you can find percent compositions from the empirical formulas of compounds by basically doing what we did in the last section, and then this additional step where we divide the amount of a particular element by the full amount. I want to point out a few things to be aware of as you're doing this to avoid any mistakes. One is that when you're doing an element that has more than one atom present, so in this case hydrogen, remember that you're including the amount for all of them together. So here we're showing 3, so times 3. So you're dividing the full amount. You're not just doing 1.008, you're doing all 3 of them. Okay, so make sure you're doing that when you have more than one. The other thing you can do is you can check your work. If you do it for each of the elements in the compound, they should add up to 100%. So that's one way you can check if you're on the right track. If you want an example, I would actually recommend going through and doing this example and then check if you're on the right track before then moving on to some of the worksheets on this subject. We also can find the empirical formula. So we're essentially reversing the process here. So what we're saying here is if we know the percent composition, we can go back and find the empirical formula. And this is the one that will often be how we would apply this in lab. So within the lab, we might be able to know what is the mass of each of the things in a compound and use that to determine the formula of the compound. So this is where we're getting to the point of sort of reverse engineering the laws that underlie Dalton's atomic theory. But now knowing the mole concept, the math is actually quite a bit easier than what they had done back in those days. So let's look at an example here. So if we had this mass of carbon, we can find how many moles we have. So again, we're applying the ideas from section 3.1 here. So convert from grams to moles. So we have 0.142 moles of carbon. And we're also given a mass of hydrogen, so we do that one as well. We do that conversion and we get 0.284 moles of hydrogen. So what you're getting here is the specific number of moles from the masses that you were provided with. What you want to do from here is to come up with a chemical formula. And we're showing here, with these numbers, but in the chemical formula, you typically want to have whole numbers, and we can get to that. The whole point of the chemical formula is a shorthand for the ratio that we have. So what we do is for each of the elements, we divide it by whichever one is smaller. So we have 0.142, we have 0.284. The 0.142 is smaller, so we divide everything by that. So 0.142 divided by 0.142, of course, is just going to be 1. And then here, when we do this division, we'll get a 2. Okay, so we end up with CH2 as the empirical formula for this compound. One thing I want to mention before we go any farther is that when we do this for data in the lab, you will often have small experimental errors, nothing that you need to feel bad about. That happens to everybody. And you might end up with something that is not exactly a 2 here. So let's say you had, instead of a 0.284, you had a 0.283. In that case, you might end up with something like a 1.99 instead of a 2. We know that is actually supposed to be a 2, so we would round that up and call it a 2. So just be aware when you are doing these calculations, if it doesn't come out exactly to a whole number, you can often round if it's very close. If it's not very close, that's what we'll be discussing next, is how we would go about making that kind of a calculation. Okay, so here we have an example of a compound, and they're giving you the masses, so 5.31 grams chlorine, 8.40 grams oxygen. They're not showing the process of coming to the moles, but if you want a bit of practice, you can do that. So convert chlorine to moles, oxygen to moles, similar to what's done up here, except of course you would have chlorine and oxygen instead of the carbon and hydrogen. So feel free to do that, and what you should end up with is what they're showing here, 0.150 um, moles of the chlorine and 0.525 moles of the oxygen. We would do the same thing. We would divide by the smallest number, which is the 0.15. So we do that. And what you end up with here is not a whole number, like a 2, not a 1.99, but a 3.5. So are we allowed to round up a 3.5 to a 4? We're actually not. If you have something like this, what you want to do is figure out what would you multiply this by to get a whole number. Okay, so if it's a 3.5, obviously we would be multiplying by a 2. So when we do that, we multiply everything by 2. So we would multiply this by 2 as well as this. So we would end up with Cl2O7, and that would be the empirical formula for this compound. So when you have a situation where you are not really close to a whole number, you need to figure out, well, what do I multiply this by so that I do end up with a whole number? So let's go ahead and summarize the process for finding empirical formulas. It's a little bit more involved than for finding the percent composition. So for each of the atoms in the formula, we're showing 2 here, but you could have 3 or 4 or more depending on the compound. You have the mass, you convert to moles by dividing by the molar mass. Okay, you do that for each one of those atoms. And then you get things in terms of moles of each atom. You compare all of those, divide by whichever is the lowest number. Okay. When you do that, you'll end up with a mole ratio. Hopefully, it's a whole number. If it is not a whole number, convert it to the lowest whole number ratio by multiplying each one of these by some whole number to get whole numbers for everything. So that's how we would go about doing that kind of empirical formula calculation to find the empirical formula. I would recommend looking at some examples. So we have an example here, and we have some on the worksheets as well before moving on to the rest of this section. So go ahead and pause the video if you can before moving forward. There's a connection again between empirical formula and percent composition, as hopefully you've recognized already. If you have not a mass but a percent composition provided, you can essentially do the same thing that we've just talked about in terms of deriving empirical formulas by treating those percent numbers as if they were masses. So for example, if you had 27.29%, you could call that 27.29 grams. 72.71%, you would call that 72.71 grams. And then you would go through and you would do your calculation, the same as we've done before. So there's some examples of that as well. So again, feel free to go through those. The last concept in this section is the derivation of molecular formulas. So just as a reminder, molecular formulas are only possible for covalent compounds, and they are showing the ratio, not just the ratio, the empirical formula is the ratio, but they're showing the specific number of atoms of each element that is present in the formula. So it's an absolute number as opposed to a relative number. So we can actually find molecular formulas in some cases if we have enough information. And how we do that is we compare the molar mass of the compound, or we can even use the term molecular mass because, again, these are only for molecules, to something that we're going to call the empirical formula mass. Okay, this is essentially what we've been doing as we are finding this information is the empirical formula mass. So you take the empirical formula that you come up with and you find its molar mass. And then we divide those two. So molecular mass, I should say, divided by empirical formula mass, and you get some whole number n. And what you'll do with that is you'll take the empirical formula and you'll multiply each thing in the formula by whatever you come up with here, whatever this n value is. So if you have substance A with a subscript x, substance B with a subscript y, you would end up with A on the subscript n times x, B and the subscript n times y. So that's how we would go about finding that. Let's look at a quick example of how this might work. So let's say we have a compound and we know its empirical formula is CH2O. And so what we would do is we would find the empirical formula mass by adding these together. Again, what we did in the previous section. And it's about 30. So carbon, 2 hydrogens, and oxygen. You can, in these situations, round it, to, basically 0 decimal places, because those additional things will not really matter in terms of doing this sort of a calculation. We're also provided that its molecular mass was 180. Okay, so this was found with one experiment. This was found with another experiment. So what we do is we take 180 divided by 30, and we get 6. So what that means is whatever the empirical formula is, we have 6 of those. So we can write it like this to help us figure it out. So CH2O, all of that in parentheses, and then subscript 6 outside of the parentheses. We multiply that through, we have C6H12O6. Okay, so this is how we find the molecular formula if we are provided with the empirical formula and the molecular mass. So we have to be given the molecular mass and the empirical formula in order to do this. In some cases, you might be given information from which you find the empirical formula, and that would be similar to things we've done previously in this section, before then going on to finding the molecular mass. Again, there will be an example here. Please look at the example. By that I mean go ahead and do the calculation. So look at this part of it. With this information, see if you can solve the problem before looking at the solution. There will also be some worksheets on Canvas that you can practice. And what I would recommend as we start getting into some more of these calculations is ask questions on specific worksheet questions if you would like to have a video made showing how to do those sorts of calculations. So please raise those questions if you have them, and I might be able to make a video solution for specific worksheet problems. That is the end of Module 3.2.